So now we're going to introduce the concept of polarity. So in this video there are three main vocab words that we need to pull out. The first is nonpolar, the second is polar, and the third is a dipole moment. So polarity is all based off of the concept of electronegativity, which I'm going to abbreviate with an EN. And remember, this is a representation, this is a value that measures how badly, essentially, atoms want electrons. More specifically, it's the amount of attraction that atoms have towards electrons. And we know that electronegativity increases on the periodic table as you go up a column and to the right on a period across a group, except for the noble gases, which we can see over here, except for xenon, they essentially have zero electronegativity because they already have a full valence shell. They don't need any more electrons, while fluorine has the highest electronegativity. So this is going to cause issues when we have covalent molecules. Because remember, Lewis structures, all these bonding molecules that we're drawing with bonding that are covalent, have nonmetals in them. And in nonmetals, electrons are shared. There is no transfer of electrons. So as a result, this electronegativity is going to play a difference. So for example, here are two molecules. Let's start with hydrogen, H2 first. If we drew the Lewis structure for hydrogen, it would look like this. And remember, this bond here represents two electrons that are being shared between those two atoms of hydrogen. Now, if we look at the periodic table with the electronegativities, we see that hydrogen has an electronegativity of 2.1. And since both these atoms are the same, and they have the same electronegativities, they're essentially pulling on these electrons here with equivalent attraction. Because remember, there's a positive nucleus in this atom and a positive nucleus in this atom. And they're both pulling on this electron here and this electron here equally. Kind of think of it like a tug-of-war. Both atoms are pulling on those electrons. So if we created an electrostatic potential map, we can see here that there is equivalence, the same color all over. There's equivalent attraction. Electrons are roughly can be found equally in this bond. On the other hand, if we had a molecule like HF, okay, hydrofluoric acid, we see that fluorine has electronegativity of 4 compared to hydrogen's 2.1. So as a result, fluorine has a greater electronegativity, which means that it pulls more on electrons. So as a result, these two electrons that form this bond here are not equally shared between hydrogen and fluorine. They're getting pulled more towards one side, towards one atom, in this case the more electronegative atom. So if we looked at the electrostatic potential map, we would see something that looks like this. The red, remember, represents more negative charge, and blue represents more positive. And well, why is that happening? It's because these two electrons, if we were to try to draw like a little spread of what the electron charge looks like, it's kind of more around the fluorine and less of it around the hydrogen, whereas here it's kind of equivalent amount of distribution of charge. So we have more negative charge getting pulled over towards the fluorine. This does not mean that the fluorine is negative and the hydrogen is completely positive. Because remember, electrons were not transferred. That happens in an ionic compound. That's when we form something like Na plus and F minus. That's not happening here. Here we just have an uneven distribution in pull. Okay? Uneven distribution. And one way that we need to notice that that is drawn, we'll see some notation for that in a second. But that uneven distribution of charge is the definition of something that is polar. It's an uneven distribution of charge in a bond, in a covalent bond. So a polar covalent bond is a bond where there's an uneven distribution of charge, and the reasoning for this is because of electronegativity differences. Okay. What is a nonpolar covalent molecule? A nonpolar, just think about the prefix non means not. It's a not polar molecule. So it has an even distribution of charge in a bond. Okay? So if we think back to the examples before, the molecule that would have been polar would be the molecule that has an uneven distribution because the electronegativities are not the same. So that would be HF in this example. And the nonpolar molecule, H2, because there's even distribution here, would be H2 and HF. So those are examples of polar and nonpolar covalent molecules. One other thing that we need to know is there's another way to represent this charge. So if we took the same molecule HF, we know that this is what it looks like with the electrostatic potential map. If we drew the Lewis structure, it would look like this. What this is telling us in the diagram is there's a slight negative charge over on this fluorine because it's more electronegative. So the way we would label that on a bond is we would draw a little delta negative and a little delta positive. So this is a delta, which essentially means the word slight. It's a slightly negative charge and a slightly positive charge on the fluorine, on the hydrogen, excuse me. It's not completely negative and completely positive because an electron has not been transferred, but the pull, the distribution is different between these two atoms. So since this molecule is polar, it has what is called a dipole moment. A dipole moment, okay, shows direction and orientation of polarity of the molecule, of the uneven distribution of charge. So the way we draw that is we draw an arrow on the bond where the positive side, it looks like this, and the positive side is next to the less electronegative atom. Another way of saying that is the slightly positive atom. And the arrow is next to the more electronegative atom, which is the slightly positively charged atom. So for example, let me just give you another one. Like, let's say you had HCl here. I would just tell you that chlorine is more electronegative. So the way we would draw the dipole moment would be like this. So this is going to be important when we're determining polarity of molecules, which is coming up in a second. So first, let's do a quick check. Given the periodic table below, which shows electronegativity values, which bonds would be considered polar? Okay, so polar means uneven distribution of charge. So which bonds would be polar? Okay, so first let's talk about CO. Doesn't matter if it's a single, double, or triple. Let's find the electronegativity values. First, for carbon it's 2.5, and for oxygen it's 3.5. Those are not equal. So as a result, oxygen is going to be slightly negatively charged because it has a greater electronegativity. Carbon would be slightly positive. So the way I would draw the dipole moment would be like this. I could also use these symbols and put them on the bond. Either way shows the polarity. Go ahead and try the next two for practice. Okay, well with CS and CF, let's look at the electronegativities. So for CS, we'll erase these here. Okay. For CS, we have carbon with 2.5 and sulfur with 2.5. So those electronegativities are equivalent. Okay? So this would be nonpolar. This bond is nonpolar. Carbon and sulfur are pulling on those electrons with equal strength. Lastly, carbon and fluorine, okay, 2 and 4.0. So fluorine would be slightly negatively charged, slightly positive for carbon, so we would draw a dipole moment pointing towards fluorine. In these examples, they're both pointing to the right. They don't have to point to the right. They need to point towards the more electronegative atom. What if I don't have this periodic table with the numbers? It doesn't matter, because you know the general trends going up and to the right, so we can figure out which element would be more electronegative. The only way to know for sure if they have the same electronegativity if it's the same atom. So if you had H2, Cl2, F2, O2, those would all be nonpolar. But how does this apply to molecules? Because we're really talking in chemistry about just two atoms. So for example, methane, CH4, has the Lewis structure like this. Okay? But we now know from our molecular geometry that, this, for example, is not a 90-degree angle. It's actually a tetrahedral molecule here that has a 109.5 degree angle, bond angle. So if we were to look back at this periodic table, we see the carbon 2.5, hydrogen 2.1. So carbon is more electronegative. So as a result, it's going to have a slight negative charge, and hydrogen will have a slight positive charge. So the dipole moment for this bond would look like this. But that's not the only bond in the molecule. There's also one here. So there'd be a dipole moment like this, and one like this, and one like this. So there's actually 4 dipole moments in this molecule. But is this molecule polar? It's actually not. Okay, methane, CH4, is nonpolar. And the reason for this is because all dipoles cancel out. They all cancel each other out. So for example, this one that's pointing to the right gets canceled out by this one that's pointing to the left. So if we were to add these two vectors together, if you want to connect this to physics, this and this are going to turn into nothing. Another way of thinking is it kind of like -1 plus 1 is equal to 0. It's the same kind of idea. The vectors pointing in the opposite directions, they cancel each other out in terms of strength. So the way to figure out if molecules are polar, you want to look for symmetry. Okay? Because here this molecule is symmetrical. We can cut it in half and it looks the same on both sides. So as a result, the molecule is going to be polar. Now this rule doesn't always work because molecules are three-dimensional. Remember, this is tetrahedral. So the dipole moments are kind of not really pointing directly at each other even. They're pointing in these 4 different directions. But since they're pointing in equivalent directions in terms of angle, they essentially cancel each other out. I know I realize what I'm saying is kind of tricky and kind of complicated. You want to know, like, okay, Mr. Shar, how do I just figure out if something is polar or not? It just takes a lot of practice. And you'll start to just get familiarity with how to apply this rule of symmetry to different examples. So for example, CH3Br. The first step is to always draw the Lewis structure. So CH3Br, carbon in the middle, it's going to look like this. H, 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 and Br. Boom, 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 boom. So I know on the periodic table from before, carbon was more electronegative than hydrogen, so there will be a dipole like this, and a dipole like this, and a dipole like this. What about this carbon-bromine bond? Well, bromine on the periodic table is further to the right than carbon, and lower down. It's going to have a greater electronegativity value. Let's just double check from this periodic table. Yep, it's about 2.8. So there's going to be a dipole pointing in this direction. It's very obvious to see from the Lewis structure that these dipoles don't cancel each other out. And if we look at the three-dimensional model, we can see that this molecule, while symmetrical, if you cut this in half, it is symmetrical. The dipoles don't cancel each other out. So as a result, this molecule is polar, and it has a net dipole pointing in this direction. By net, I mean sum. A net dipole equals the sum, kind of the overall dipole of the molecule. So as a result, there's a slightly negative charge here and a slightly positive charge on this end of the molecule. What about NH3? So for NH3, the Lewis structure would look like this. Again, this molecule is symmetrical. We would have a dipole. Okay, so let's see, nitrogen is 3.0. Hydrogen's 2.1, so pointing more towards nitrogen. So we would have something that looks like this, and this. Again, while this molecule is symmetrical, we can see that the dipoles don't all cancel each other out. And in fact, since there's this lone pair of electrons, that means we have negative charge up here. So as a result, the net dipole would be pointing up towards and through that lone pair of electrons. So this nitrogen side, the nitrogen atom would be slightly negative, and this bottom middle would be slightly positive. Last but not least, let's try propane down below. This one's a little trickier because it's not just one central atom. This is what the molecule looks like. Okay, C3H8, boom, boom, boom. It's too complicated here to probably go through every single bond and consider if every single one is polar or not. You could, and if you did, you'd see that, okay, this hydrogen-carbon bond is going to cancel out with this one. This is nonpolar, nonpolar. This will cancel out with this will cancel out with this, and this one will cancel out with this one. So as a result, since all these bonds are essentially equivalent, even though this molecule might look a little funky, this is actually going to be a non-polar molecule. And I forgot to label that this one was an example of a polar molecule. So C3H8, non-polar. Okay. Hydrocarbons, CHs, CXHY, hydrocarbons are almost always non-polar. Okay. As kind of a little rule if you want to think of it. Otherwise, it just takes practice of drawing the Lewis structure, thinking about the dipoles, do they cancel out or not, and going from there. Now, last but not least, the most important molecule we need to consider is water. Because if we drew the Lewis structure for water, H2O, okay, water looks like this. If we drew the Lewis structure, we know that's not the correct shape. A more accurate shape would look like this, okay, HOH with a bent geometry. And as a result, we need to think about the dipoles. Okay, well, one dipole is going like this, one's going like this. Are those canceling each other out? Not exactly. They're not putting directly at each other. As a result, there's a net dipole. In which direction? Kind of pointing up like this. Okay, they both tend to be pointing slightly up. So as a result, that indicates there's a slightly negative charge on oxygen and a slightly positive charge on the hydrogen ends. Why is this important? Well, because, don't worry about these hydrogen bonds yet. We'll talk about that next week. As a result, this is a slightly negative end and this is a slightly positive end, which means if you put multiple waters next to each other, we know positives attract negatives. Okay? So the slightly negative of this oxygen will be next to the slightly positive end of this hydrogen, and on and on and on, and we'll create this network. So in terms of polarity, what's important is this positive and negative charge allows us to determine how molecules will orient themselves, how they will get next to each other so that their positive and negatives attract. And this is super important in water, which is very, very polar, which you might not predict based on this Lewis structure. A very common misconception. Student draws this Lewis structure, thinks these cancel out, but they don't, because that's not the shape. The shape is actually bent. So watch out for that. The very last thing is a little rule of solubility that says like dissolves like. What this really means is similar polarities dissolve in similar polarities. So for example, if in a beaker you had H2O, which we said is a polar substance, and you dropped in C3H8, which we said before was nonpolar, these will not dissolve because they do not have similar polarities. Like dissolves like means that if you have a nonpolar substance, you would need another polar substance like CH3Br from earlier. This would dissolve in water because they're both polar. And that has to do with the fact that they will be able to arrange themselves so that positive and negatives are oriented to each other. So we want to be familiar with this phrasing of like dissolves like. It's not a rule that you can use to explain why some substances dissolve. You need to explain it in terms of the polarity, but it's a way to remember it. Whew, we've covered a lot. That's what we need to know about the polarity of bonds and molecules.